Alright, so this audience is super broad. We start from particle physicists, astrophysicists, astronomers, cosmologists, theorists, observation, and this is like kind of a topic. It's an astroparticle physics topic which bridges lots of different things, right? So I'll try to make the talk as simple as possible, and if you are not able to understand anything, please ask, all right, and I'll be happy to answer. All right. Okay, so I'll first discuss the concept of in-depth detection of dark matter. Some of you may know about it, but many of you may not know about it. I'll discuss what that is in a few slides. I'll introduce James Webb Space Telescope. There were super exciting talks about James Webb Space Telescope observations in this conference. I'll just give a brief overview in case you have missed it. Then I'll be talking about what do we do in order to search for dark matter, and then I'll conclude. All right, in-depth detection of dark matter. What is it? Well, okay, so this is an obligatory slide of dark matter. I'll just spend 30 seconds on it. So as you know, so if you look at the universe at various length scales, from the scales of dwarf galaxies to the CMB, there are gravitational anomalies. And the way I think about it, dark matter is the most minimal solution to all those problems. You put something like dark matter, all those problems are solved at one shot, right? And these are the gravitational curve, bullet cluster, the cosmic pie chart, and things like that. The point is that we know dark matter definitely interacts gravitationally. We do not know if dark matter has interactions, has any other kind of interactions. That is, does it interact under any other force? And that is what we are trying to go for. That's what I'm trying to go for in this work, right? And that is super important to understand the nature of dark matter. So although we have actually discovered dark matter for probably 100 years, if you think of Zwicky, even more than that, a very nice review of history of dark matter by Dan Hooper and Gianfranco Bertoni, but still, instead of doing this awesome work, we have made some progress. Just by using gravity, we have made some progress that anything which will be dark matter can have this mass range starting from 10 power minus 22 eV to about a few solar masses. Right? And in this conference, we have had talks of all this context. Right? So the lightest range, Bihag and Gaurav gave some awesome talks. Then there were talks on axions by Harsh, and the light dark matter WIMPs and primordial black holes. There were too many talks to list. Right? Yet, so this is one important thing. Just by using gravity, we know what can be the mass range. So that's an optimistic view. The challenging view is that, well, it's still 90 orders of magnitude, and we do not know how to do it, right? And it's almost certain that gravity alone cannot figure out this thing. It's not guaranteed, but it's almost certain. So the way I talk about this is that, first of all, we need to test all well-motivated candidates, and it's important to test all regions of dark matter parameter space and all different couplings of dark matter standard model particles, all right? And that's what we'll do. We will be considering axions, more precisely QCD axions. All right, so what is the idea of dark matter indirect detection? So the idea is very simple. So you look at a distant part of the sky where there is dark matter, right? I mean, it can be the galactic center, it can be dwarf galaxies, it can be galaxy clusters, it can be the whole Milky Way halo, all right? So this is the telescope, and then you hope, so this is the thing that you're trying to test, that two dark matter particles will come together, will annihilate, and produce two standard model particles. So dark matter goes to SM. And there is some Feynman diagram that's happening inside which we do not know, which we want to know. Or dark matter will decay into two standard model particles. Right? Again, some Feynman diagram which we do not know, right? And we want to know. And this is actually done to search for dark matter annihilation and decay into all kinds of stable standard model particles. Right? Note that you can also have three dark matter particles interacting and producing it, but I'm talking of the simplest possible scenario. All right? So what are the stable standard model particles? Well, there is gamma rays for photons in general, neutrinos, positrons, electrons, protons, antiprotons, and things like that. Also sometimes nuclei. And our hope is that at some point there is this cartoon. We will make it with real data. The cartoon will consist of, in the x-axis, energy of stable messengers. The y-axis should be the event rate. The astrophysical background will be like this, which will be falling, and dark matter will give you a peak. Dark matter has to give a peak because dark matter is non-relativistic. So when it either decays or annihilates to standard model particles, you generally have this cutoff at this mass energy. All right. So we can use these spectral features, and people have used all kinds of targets like the Sun, Milky Way, galaxy clusters, cosmic microwave background, using all flavors. All right. And there, for example, Shantanu has worked on with real data to do this search. All right. Now, if you think about it, how does this work? How do you search for the signal? So this is the formula. This formula is actually very simple, except that it has a lot of complicated details. All right, so let me go walk through it. So this is on the left-hand side is the flux of particles. So as we talk, for this equation, this is only neutrinos. That is simply because for photons it's essentially similar unless you're going to very high energy gamma rays. For charged particles it's horrendously complicated and we don't know how to solve it, but we can make some progress. So this is a flux of say neutrinos which are coming from dark matter per unit energy, per unit area of the detector, per unit time, per unit angle from the sky. This obviously depends on, if I talk of dark matter annihilation, it will depend on the annihilation cross section, the sigma v. Well, I mean there are two dark matter particles coming close to each other, so it must depend on the number density squared. So the dark matter density rho divided by the mass of dark matter square, number density square. Yeah, thank you. And it must depend on what is the spectrum of the particles that are coming in from this annihilation, and it must also depend on this integral which tells you I am sensitive to all dark matter particles that are in my line of sight. Everything that is in my line of sight, right? This is for dark matter annihilation, for two particle dark matter annihilation. This is for dark matter decay, the same thing except that there is a lifetime of dark matter here, alright, and it's not rho square, it's rho by mdm because there is one particle decay. Note that this first part is particle physics, how is dark matter interacting with Steinwall particles, particle physics, and the second part, how is dark matter distributed in the universe, that's astrophysics / cosmology. So this is where the thing is, alright. And the kind of and the detector that will be used is James Webb Space Telescope. Again, there were lots of excellent talks. So just to orient other people if they were not there, so in this electromagnetic spectrum there is Hubble, and then James Webb Space Telescope is an infrared telescope which covers this wavelength band. For particle physics, I'll come to that. What is this? It's basically EV scale, 0.1 EV to 5 EV scale. Right? For an astronomer, it's 600 nanometers to 28,500 nanometers, and then there was Spitzer. Right? So it's in the IR range. Right? It was flown for doing various things, early galaxies, exoplanets, and things like that. What we were trying to do is, can we actually do dark matter with it? So there are four different instruments on board JWST. There's NISPEC, which is near infrared spectrograph. So that means you see the spectrum. For particle physics, that means you are measuring the spectrum. You can measure the lines. All right. There's near infrared camera. Again, for particle physics, this is just taking the picture. You just take camera of all photons. You don't know the wavelength very well. All right. You have a band of wavelength, right? Whereas in spectra, you see the individual wavelength very precisely. MIRI, which will not use, will be using mid-infrared instrument, and that's NIRIS. Right. And the important thing, again, in case you are not very used to JWST thinking, the reason why it's so sensitive is because its mirror is huge. All right. So this is the Spitzer mirror size, Hubble mirror size, Webb mirror size. All right. And if you think of particle physics, it's basically the number of photons that the sensitivity will depend on how many photons you detect, which obviously depends on the mirror size. Right. If you think of particle physics, cross sections and things like that. That's why it is so sensitive. Right. And there have been wonderful talks by various people in this meeting. All right. So as you guessed, when I said earlier, if you think about it, I said that will give a very sharp cutoff. So we need a very sharp resolution. So imaging is not very useful, right? If I take a broad wavelength range, it will not be very useful. It will still be useful, but it may not give you leading limits. That's what we wanted to do when we started the work. But spectroscopy, which gives you fine details of the photon spectrum that is entering the detector, will be useful, and that's what we'll use. We'll use the spectroscopy. All right. So this is an example of the flux on the y-axis and the wavelength on the x-axis, and this is what you can get from this website. Right. So we will use the spectroscopy because we are actually searching for a dark matter line, as I'll say very soon. So just to give some numbers, so NISPEC has a wavelength range of 0.6 to 5.3 micrometers. Again, for particle physics, what does it mean? It means 0.037 electron volts to 0.33 electron volts. Right. It has a field of view 3.4 cross 3.6 arc minute. It has a fantastic energy resolution. Energy resolution, but anyways, the wavelength resolution 2700. And the easiest dark matter search, you can do lots of complicated dark matter searches. The easiest dark matter search that you can do is to say that, well, the number of photons from dark matter should not overwhelm the number of photons JWST has detected. That's it. Full stop. That's the bare minimum we can ever do. All right. And that's what we have done. And you see that we can actually get world leading limits on that. So the JWST till now doesn't have a dedicated dark matter search program. So what we did is I will show you how we used other data to pull this thing out. And then we'll try to say this. All right. So this is the main idea. Right. So this is the cartoon. So this is the Earth, right? JWST is flying in the L2 point. This is the dark matter halo. Whenever JWST is looking at a distant object, that means an extragalactic object is looking through the Milky Way halo, through the Milky Way dark matter halo. You cannot remove it unless you explicitly remove it, right? So that's guaranteed. So what is happening is if there is dark matter in the Milky Way halo decays to 2 photons, it will show up in the signal, right? So in in other words, if you look at a distant object, this will be the wavelength flux I'm talking picture, and dark matter will show up as a line. Right? Remember, dark matter is non-relativistic. So if it decays to 2 photons, the wavelength will be this. For a dark matter mass of electron volt, it will be 2.49 micrometers. Right? This is, again, it's a sort of a mixed thing because again there's a wide range of audience here, so you can pick how this works. Right? For dark matter, for particle physics, it's very easy. Lambda is just half. For astronomers, 2.5 micrometers. All right. So the point is to search for unidentified lines in the JWST spectrum. Turns out that remember, the signal is for us is the foreground, and we have to use data where the foreground has not been removed. Right? For example, when JWST looks at point sources, they do remove the foreground by doing something called NOT and dither. Right? We will not use that. So we'll be using technically what is called the extended sources and things like that. All right. All right. So this is an example of what we are trying to do. Let's take a dark particle of mass 0.7 electron volt. And its coupling into photons is given by these units. 2 times 10 power minus GeV, some units, right? Doesn't matter. So it will decay to a line. So wavelength on the x-axis, flux on the y-axis. This will be the thing. If I look at this direction, this is some quasar, this direction, right? And this is the continuum spectrum in that direction. It will just look like a blazing signal, right? This data point is not yet ruled out by any other experiment till now, right? So this is basically how we started. And these are the various in the map of the sky. These are the various astrophysical objects that JWST discovered that we could get from Mars. Alright, so you can see importantly all of them, so this is in the galactic coordinates, all of them are away from the galactic center. So dark matter profile uncertainty does not play a role here. Alright, and although we have 267 sight lines, about 20 of them are important because they give the strongest bounds. Right? Now, 1 minute of particle physics. Okay, so I've been talking about dark matter decaying to 2 photons. You can ask, well, does any good particle physics model gives? So this is already introduced a bit by Juhi. So probably one of the most well-motivated dark matter models is the QCD axion dark matter. So why is the QCD axion important? So well, if you're a particle physicist, this Lagrangian may look very simple. If you're an astronomer, this simply states that if you have a neutron is composed of quarks, right? So it has a UDD, right? But it has a vanishing dipole moment. So that means the quarks are on top of each other. Why? Or the quarks are very symmetric, right? Why? Again, this I'm just saying this in a very simple way, but you can do this whole map, take this Lagrangian and you can calculate this, right? In a Feynman diagram manner. So why are the charges either on top of each other or why are they so aligned to each other? This is a question. That means this parameter theta, which is the free parameter, must be extremely small, and this is something we don't like. We cannot have an extremely small parameter. There are deep particle physics reasons for it, right? We have never seen parameters be as such small. They should be of order 1. They cannot be 10 power minus 2, for example. There must be a reason. So there are many solutions to this, what we call the strong CP problem. CP means charge and parity. Let's ignore that, what that is, but anyways, it's an important problem. One of the problems is basically you have an axion. The potential looks like this, and then this whole thing will be, the potential you have to make this to be 0, so then this whole thing will go to 0. That's what it is. One sentence, right? And you can show that these axions can be dark matter, right? Note that this is coupling to gluons. This G mu, G mu, these are gluons. So this has a specific mass. This has a specific mass range, which talks to which is connected to the pion mass. Right? So you can basically talk about the mass of the QCD axion as like this. Right? You can, so this Fa is a free parameter. You can keep on changing it. It will give you some range. Right? Typically very light. And if you have this Lagrangian, as I said, axions, in addition to coupling to gluons here, will also couple to photons, or almost all axions to it, unless you really fine-tune parameters. You can have this Feynman diagram, right? I mean, if you don't know anything about particle, you don't have to worry about it. It just says, what does this say? This says A is coupled to 2 photons. So forget this triangle, A can decay to 2 photons. That's it. Alright? Besides this motivation of QCD axion, you can also have just axion-like particles. This is something that is predicted in many string theory models or grand unified theory models, right? Where you just have this coupling. This entire story that I said earlier about coupling to gluons is not there. Alright? This is predicted. So this is sort of an extremely well-motivated scenario to search. And there have been many papers which explicitly shows that QCD axions on ALPs, axion-like particles, that means they only have this coupling, can make up the entire or a substantial portion of dark matter density. So one of the recent papers is by David Simpson at this side. Alright, so this is the global picture of the axion x-axis is the mass of axion. This note that is not coupling, it goes to lower masses, and this is the coupling Ga gamma gamma, right? Anything that you see colored is ruled out, right? And this yellow, these are some theoretical models. This case PZ and DFSZ, named by people who actually first proposed it, right? So these are some. This is a theoretical band, which is well motivated, and all of these regions are ruled out by various experiments. I can tell you all of them, but let's do it later. All right. So let's do some very simple thing. I said if ALP decays in 2 photons, the wavelength will be this. This is straightforward. The decay rate will be this. This is also actually straightforward. Even if you don't know any particle physics, you can say by dimensions it must be Ga gamma gamma square everything. Just by dimensions. And then you have to do a complicated Feynman diagram calculation, you get a factor of 64. That's nothing. Right? And again, if you're particle physics, you can do this calculation. This is fun calculation. The differential flux of photons will depend on this, which will obviously depend on something called the D factor, which tells you how much dark matter is there in the line of sight, and depends on the decay rate of the and then there are other factors, geometric factors, and things like that. You have to also make sure that because JWST angular resolution is so good, it's aligned to be thickened with the dark matter velocity distribution and the energy resolution. So that's what we do in the lambda, right? And then we sort of use it in the data. As I said, what we do is we take the continuum region. That means we don't take the region where there are bright lines. We take the continuum region. We do a simple spine fitting, and then we add a try to search for this function. That's what we do. Yeah, okay. All right. And then we just say just like this. So what does this plot tell you? This plot tells you by looking at this sight line, that matter cannot get into the axion with mass 0.7 eV and this part. This is what this tells you. Because otherwise we overshoot the data, right? For a factor of 4 or 5. Right? That's what it is. That's what we have done using some chi-square and things like that. And this is our limit in our cartoon way, and I show you the real limit. So the x-axis is the mass of axion, the x-axis in eV, electron volt. This is Ga gamma gamma, right? This is the coupling axion. This line that you see, this straight line, is coming from globular clusters. Basically, if you have these axions, your stars will cool very fast. So anything above is ruled out of this line. Is ruled out from globular cluster age region. This is coming from a telescope called spectrograph called Wine Red, which looked at 2 dwarf galaxies. They did not find it, so they ruled out anything here. Yeah, just before our work, there was this paper by Janish and Pinetti where they used the GN-Z11 observations by JWST to rule out this region. In this region, this is the DFSZ that I said initially, some very motivated thing. And as I said, axions do come from various string theory and grand unified theory models, and they claim that it can be this entire parameter space, this yellow region that you see, E by N. These are some particle phase parameters in top of it. Right? Our results is this. Anything within this thing is ruled out. So you can see there is at least here in the entire range, we have some completely named limits, which is not done by any of us. So this is the real thing. JWST data is dirty. Not dirty. It's very lots of spikes and things like that. So depending on which diffraction rating you take, G395, G235, G140, these are the limits. And then the older one is Wine Red and globular cluster and JWST. And again, this thing is something that is motivated from string theory and grand unified theories. So I just went through so this is there in this paper. A day before we put out a paper, there was another similar result by Elena Pinetti. Her results are a bit stronger than what we have, and we are in discussion with her to see where do we have the differences. As I said, there was an earlier paper by Janish and Pinetti, and there was a projection by Sandeep Roy. And then there was some theory things trying to do. Right? So the bottom line is we are able to prove a new mass range for ALP dark matter between 0.47 eV and 0.78 eV, and between 0.47 eV and about 2 eV, we have the whole leading limit. I mean, we are the Pinetti put together. Alright, and so I'll conclude. I hope I have convinced you JWST, not just me, others are convinced you probably better than me, that JWST has opened up a new infrared view of our universe. Given the leading sensitivity, we wanted to do a dark matter search, and using the simplest possible scenario that the flux of dark matter photons should not exceed observations, give us leading limit of axion-like particles or QCD axions decaying to dark matter in this mass from 0.47 eV to 2.55 electron volts. And this is able to probe some models from string theory and grand unified theory, and we hope that with more data, we will either be able to discover the QCD axion dark matter or rule out other ranges of